Space is vast. How do we know the universe has 3 dimensions? How does nature tell us about what we see? And probably the most uncomfortable question is, what if dimension depends on how we perceive reality? Figure It Out presents Why Do We Think There Are 3 Dimensions? In the beginning, there was light. The Big Bang brought the universe to life, and with it, a lot of heat. And after billions of years of cooling, we have the Earth with snakes that see heat, bats that hear sound, fish that feel pressure, and humans that observe light. But as the world turns and things start heating up, we begin to wonder just how so much random energy creates a distribution, a pattern, one that may have less to do with geometry and more to do with information and how the universe has conversations. When heat spreads out, it fills the entire space. It diffuses in a rather uniform way. But the shape of the box in which it is diffusing in tells us something about the dimension. If we bring 2 metal pieces together, one hot and one cold, we begin to see how the energetic particles share their heat, with the colder particles becoming more energetic, and the longer that they interact, the more diffusion takes place, which you can see is an averaging effect, where every particle is averaging to an equilibrium temperature. In fact, this doesn't just happen in solids. 2 gases brought together, like hot air and cool air, will diffuse in the same way. As if you opened a door between a hot room and a cold room, one sees that the temperature of the air begins to average as the heat diffuses. Even a simple experiment like dropping a dye into water at different temperatures shows heat randomizing the motion. Diffusion happens faster in hotter situations. Temperature moves from hot to cold. But you don't have to run any fancy experiments to know what I'm talking about. You just have to enjoy a nice cup of coffee with some nice cool milk. As the heat diffuses through the coffee, the cold milk looks as if it is moving in slow motion. It's quite beautiful. It looks like it's moving in slow motion because at first it is. Then as heat begins to diffuse, the particles nearby each other are constantly adjusting their own temperatures. They're adjusting it to an average. And eventually, if all of the particles within the coffee do the same thing, eventually the temperature will become homogeneous. That is, they will have reached an equilibrium point throughout. And so, to get a better understanding of this, we're going to have to understand how heat flows. And we're going to start this in one dimension. Consider a metal rod that is one-dimensional, a thin metal rod, and heated at one end. The heat diffuses through the metal according to the one-dimensional heat solution, given here 1 over the square root of 4 pi t times e raised to the negative x squared over 4t. In other words, it's a Gaussian function that creates a normal distribution curve like you see here. How does heat behave? Heat flows from hot to cold, and the amount of heat flow depends on how steep the temperature difference is. So, if we imagine a metal wire arranged along the x-axis, then the temperature of this wire, U, is a temperature function of both position x and time t. Temperature changes across both space and over time. Now imagine one end is heated up, and the heat will flow through the wire from the hot end to the cold end by diffusing through the wire. Fourier's law of heat conduction. The flux or flow of heat can be given by the function Q equal to negative K du dx, where Q is the heat flux, or how much heat passes through per second. K is the thermal conductivity, and the negative sign, it indicates that heat flows downhill to cooler regions. So heat flux measures how temperature flows or changes through space. If temperature changes sharply, the more strongly heat will flow, and if temperature is flat, no net heat will flow. Now consider a small cross-section of the wire between points x and x plus delta x. We consider the flow of heat through this section, heat entering in through the left and exiting through the right. If more heat enters than leaves, then the region will warm up. Conversely, if more heat leaves than enters, then the region will cool down. This is just the conservation of energy. But what if the flow going in and the flow going out have different rates? Let's say we want to measure the net heat gain. So we need to measure the heat flux going in at the left and the heat leaving the right-hand side at x plus delta x. Finding their difference means that we will calculate the heat leaving at the right side using a first-order approximation. And this difference will give us the net gain, which is approximately dq by dx times delta x. In other words, the change in heat in space over that small interval. So changes in heat flow create changes in temperature. Thermal energy stored in the segment is proportional to temperature. Now, according to physics, the heat gained is equal to rho times c times delta x times du by dt. And rho here is the density of the material, and C is the specific heat capacity of the material. Here, the metal in the wire. Now, conservation says that this is equal to negative dq by dx multiplied by delta x. And with a little simplification, we can divide out the delta x's here and get rho c du by dt is equal to negative dq by dx. And if we recall that q is equal to negative k du by dx, then differentiating q with respect to x gives us k times the second derivative of u with respect to x. And with those constants in front, we can rearrange a few things and simplify this second order partial differential equation. And so now, if we define a new parameter alpha to be equal to k over rho c, then by substitution we get this cleaner form of the equation. And so the rate of change of temperature in time is proportional to the curvature of temperature in space. Which begs the question then, why is curvature involved here at all? If curvature is positive, then recall that the point will be a minimum. That is, the point is colder than its surroundings. What that means is that heat flows inward, and therefore the temperature of that point will begin to rise. Now, if the curvature is negative, that means that the point is hotter than its surroundings and heat flows outward. The temperature will then fall. And this is where we get an averaging effect for every point particle that is experiencing heat. So heat evolution is governed by curvature. So now we've got our one-dimensional heat equation defined. And with that, we're going to consider how to solve this differential equation using the separation of variables method. That is, we're going to assume a solution of the form x times t. So when we take the partial derivatives with respect to t and the second with respect to x, our product looks as follows. Thus, when we substitute it back into our differential equation, we get this, which we can divide out by alpha x times t to get the following separated equation. Observe that the right-hand side only depends on x, and the left-hand side only depends on t, so that we can conclude that both of these are equal to a constant, and for convenience we'll choose that constant to be negative lambda. Substituting this in, we have x double prime over x is equal to negative lambda, and t prime over alpha t is equal to negative lambda. Rearranging these two equations gives us a system of differential equations. The time equation gives us this as its solution: c e to the negative alpha lambda t. The spatial equation has this as its solution: so now we have these two solutions And the general separated solution, the product, looks like this. On a finite interval, the boundary conditions force only certain values of lambda. For example, on the interval from 0 to L, with our boundary conditions here then being given equal to 0, we get x of 0 equal to 0, determining that the amplitude of the cosine function is 0, and therefore we only get a sine function out of that first part. At the boundary L, we get the sine function equal to 0, which then forces the square root of lambda times L to be equal to integer multiples of pi. And thus we can define specific values for lambda as n pi over L quantities squared for different modes n. So for a given n value, we have this solution. And the bn's are determined by the initial condition. So the general solution is an infinite sum of modes. The constant b sub n comes from the initial temperature by letting T equal to 0, thus giving us just a function of x. And so one notices that this f of x equal to this sum might be familiar. You see, this is just the Fourier sine series of f of x. And therefore, the coefficients can be calculated using Euler's integral formula. So the finite interval in the limit gives a Fourier series solution. And on the whole real number line, that is, if we think about extending the line infinitely long, the wire that is, with no boundary walls, the discrete sine waves become a continuous spectrum of sine waves and cosine waves together. The discrete frequencies n pi over L become a continuous variable, xi, and the sum becomes an integral. Thus our solution becomes this integral. And some of this notation, if you're familiar with it, is from a Fourier transform of the initial temperature, that f hat. And we also have the diffusion dampening factor, as well as the pure frequency modes in the Fourier transform. And it's the inverse Fourier transform of the dampening factor that is the Gaussian heat kernel, which we now will examine a little closer. Normal distribution curves occur because statistical distributions of random variables that cluster around an average or a mean govern the mathematics behind populations, heat diffusion, and probability. We call these normal distributions, or Gaussian distributions, mu being the mean and sigma here being the standard deviation. So what about heat flow in 2 dimensions, like on a 2-dimensional plate? Heat flows uniformly from a point, according to the heat equation given here for the 2-dimensional case, and you'll notice some subtle differences in this function from the 1-dimensional case. In fact, let's make a comparison now. If we look at the one-dimensional heat solution in comparison to the two-dimensional heat solution, one automatically notices a difference in that normalization constant. The first constant is raised to the 1/2 power, where the second constant is raised to the 2/2 power. There's something being said about the dimension in that constant. And in general, for a vector x in n dimensions, we have the n-dimensional heat equation. Which brings up a very important point. Hidden inside the diffusion of heat is the dimension of space itself. But what is the dimension of space doing here at all? For the n-dimensional heat solution, one notices that the exponent changes with dimension, the decay changes with dimension, and the normalization changes with dimension. One could say that heat literally knows how many dimensions exist. But again, why does dimension appear here at all? Well, heat does spread through volume. And it turns out volume grows differently in different dimensions. So how do you calculate the volume of an n-dimensional sphere, an n-dimensional ball? That's going to require a little calculus. The problem of computing volume. In a first-year calculus class, you learn to compute the area under a function's curve on an interval from a to b using something called the definite integral. It's a continuous sum, which gives you the area under the curve, and this can be extended to higher dimensions to give us something such as volume. We're going to use something called the slicing principle. So consider a cylinder of cheese. If you took a slice from the middle, we call that a cross-sectional area. And if we take the area and multiply it by its height, we get the volume of this cylindrical slab of cheese. So the slicing principle is utilized in the same way. If the cross-sectional area A of x varies continuously with x on this interval, then the volume of a solid can be given by integrating that area over that interval. So when it comes to slicing a sphere in, let's say, 3 dimensions, what we'll do is we'll consider the 2-dimensional analog. So the cross-sectional area, if we think about looking at the sphere straight on, so we're looking at it as if it's in 2 dimensions, we have a slice which will create a disk. That disk will also have a radius of the square root of r squared minus x squared. And thus the cross-sectional area function a of x is given by pi multiplied by r squared minus x squared, which will integrate from negative r to positive r, or from 0 to r if we employ a little symmetry. And thus we get the formula for the volume of a sphere, 4/3 pi r cubed. We can utilize the slicing principle in higher dimensions. So in R3, a radius or a line segment can have its distance calculated by using the distance formula, which is just a fancy form of the Pythagorean theorem. So in 3 dimensions, you have coordinates with x, y, and z. However, in 4 dimensions, we can extend that to coordinates x, y, z, and w, and here's the 4-dimensional distance formula. This is going to help us define a radius in 4 dimensions. The equation of a sphere in any dimension is given by the distance formula, which describes the shape of the sphere as the locus of all points equidistant from a center point. And let's make a quick distinction here. A sphere versus a ball. The four-dimensional sphere is given by the equation r squared equals x squared plus y squared plus z squared plus w squared, which is just the boundary or the edge of the circle. And if we want to incorporate the entire volume of the ball, we need to use an inequality to include all the space inside the boundary, including the boundary. So in 4 dimensions, it's pretty hard to visualize what a 4-dimensional sphere actually looks like. So we're going to have to trust the math and the slicing principle to give us the volume. Imagine that the 4D ball of radius r is laid out along the x-axis between x equals negative r and x equals positive r. For a fixed value of x, the slice above x is the set of all x, y, z, and w with the value of x such that y squared plus z squared plus w squared is less than or equal to r squared minus x squared. And with that, this is a 3-dimensional ball of radius square root of r squared minus x squared, and its volume is given as such. But remember, we want the volume of the 3-dimensional ball to be like an analogous area segment or cross-section. So in 4 dimensions, our cross-section is 3-dimensional. And so, thus by the slicing principle, the volume of a 4-dimensional ball of radius r will require us to integrate this volume in 3 dimensions from negative r to r to find the 4-dimensional volume. And again, employing some symmetry so that we can integrate from 0 to r, we have this integral to evaluate. Now to do so, let x equal r sine of theta. This is going to change our limits of integration to 0 to pi over 2. Then our square root of r squared minus x squared becomes r cosine theta, and dx is r cos theta d theta. So that gives us the integral for our 4-dimensional ball of radius r. With an integral, we have to evaluate cosine to the 4th power. And for this, we're going to employ something called the integral reduction formula shown here, where we can change the integral of a higher power down to a lower power, picking up a constant in the front that's dependent on n. So with one iteration of this reduction formula, we can reduce the cosine power down to 2 in the integral, and then apply it one more time so that the power of the cosine in the integral is 0, making it very easy to evaluate, thus giving us the volume of a 4-dimensional ball of radius r as pi squared over 2 times r to the 4th power. And for some strange reason, I expected it to be a little more elaborate. For the volume of an n-dimensional ball of radius r, we integrate from negative r to r over its surface area. So if we let the volume of the n-dimensional ball be given by the unit volume times r to the nth power, again a unit volume, a radius of 1, we can calculate the unit volume in different dimensions here from 1 to dimension 4, and we can start to track how that volume changes as we go through different dimensions. Recursively, we can define each of the volumes using this integral that utilizes the reduction formula. And if we were to think about a box that can contain this particular sphere of n dimensions, and the ratio of the volume of that unit sphere to the unit box that contains it, one notices something very strange, that both the unit volume and the ratio of those two volumes go to 0, and the maximum volume takes place in dimension 5. So with our slicing principle, one can calculate the volume of a unit or n-dimensional sphere of radius r by using the n-1 dimensional surface area to do so. And thus, if we're doing the unit ball from 0 to 1, integrating, and let u equal x squared, and then calculate dx, we get the following integral form, which may look very familiar to you. That's right, this integral is a form of the beta function. And the beta function is a beautiful integral that has a connection to another very nice integral. So our n-dimensional volume is connected to the beta function through these values. And the beta function is connected to the gamma function. And this nice relation, with the gamma function being defined by this integral, is also connected to factorials. And thus calculating the volume of the n-dimensional ball amounts to being able to calculate values of the gamma function, which you can use its recursive formula to reduce down to these two formulas, one for the unit ball and one for a ball of radius r. And it's such a beautiful formula that includes pi and the gamma function. So as we look at heat patterns all around us, from our own bodies to patterns in weather, we begin to wonder what other principles are at work when it comes to heat. And that brings us to the conservation of heat. You see, heat is neither created nor destroyed during diffusion. It only spreads out. Mathematically, if our heat distribution function is given, the total amount of heat remains the same over time, which means that when we integrate this overall space, the integral is constant. Now for our normalized heat distribution function, that constant is equal to 1. And reducing down our integral, a very curious property emerges. You see, as we evaluate our integral via the slicing principle of the surface area of n-1 dimensions, this Gaussian integral presents us with a solution. Because you see, the surface area is n times the volume of the n-dimensional ball. So replacing that in the formula gives us this relation. And once we evaluate the integral, we get this. And with a little simplification, well, what happens here is nothing short of a little bit of magic. Because again, with some simplification, what has emerged is the volume of an n-dimensional ball, which when taken to its simplest form through the recursive version of the gamma function, miraculously we obtain the formula we got earlier. The conservation of heat literally forces the formula of the n-dimensional unit sphere to appear. This is profound. Let's summarize everything that we've learned today. Heat reveals dimension. Heat diffusion in n dimensions is governed by an equation in which the dimensionality of the space is present in that solution. When we use the slicing principle to calculate volumes of higher dimensional spheres, we wind up getting a formula that involves not only pi, but the gamma function, one that is connected to factorials. And so the volume of an n-dimensional ball through calculus is evaluated to be v of n is equal to pi raised to the n over 2 power, all divided by the gamma function evaluated at n over 2 plus 1. Now, the normalization of the volume means that we take that constant to be equal to 1. And by heat conservation, what miraculously appears again to us is that the heat kernel reveals the volume of the n-dimensional ball exists within it. The heat kernel equals a Gaussian density, and the central limit theorem for normal distributions says that basically heat and anything that is generated by heat is going to follow a certain pattern as the random behavior begins to smooth out. It does so in a very specific pattern. So why 3 dimensions? Well, if space had 1 dimension, the Gaussian would be too concentrated. If it had 2 dimensions, it would be too flat. But at 3 dimensions, the Gaussian matches heat flow perfectly. From fire is born perception. The heat equation contains dimension, its solution contains geometry, its normalization reveals volume, and its form is Gaussian. The Gaussian is probability. Probability is the language of uncertainty, and uncertainty is the limit of knowledge. Knowledge is how we experience reality. And thus we see 3 dimensions because heat, and the laws it obeys, reveal to us that it must be. The shape of heat remains the same in every dimension, but the normalization changes. And buried in that normalization is the volume of the n-dimensional sphere. We are creatures born from thermodynamic processes. So perhaps we do not merely observe a 3-dimensional universe, but rather experience reality through the geometry of diffusion itself, where even our perception of time might just depend on how hot we really are.